Good afternoon, ladies and gentlemen. Welcome to this last presentation of this day. David and I would like to introduce you to the topic of the safety assessment of corroded cantilever retaining walls. And this is a joint presentation, as we are unifying here two disciplines of structural and geomechanical engineering. So after this collapse at the Brenner Highway, as we just heard in the last presentation, the Federal Roads Office conducted a pilot study to assess actually the situation for their walls. And in the end, they were assessing 56 walls out of the 1960s and the 1970s, and the result was quite alarming, since about 2/3 of these walls were then affected by local corrosion. And given the large number of retaining walls in the portfolio of Fedro, and there are more than 2,500 of these walls, the hazard potential is obviously quite high, and so are the costs. They estimated about 800 million Swiss francs to retrofit these walls over the next 15 years. But why are these walls corroding? The pilot revealed that the corrosion is located mostly just above the footing at the construction joint, and as we heard, it's not due to chlorides, but due to honeycombs out of a bad compaction of the concrete. It then formed a large macro element because, of course, the steel in the rest of the wall was passive, whereas this steel there was not passivated, and this then led to high corrosion rates and large cross-section losses. And also these numbers we have seen just in the last presentation, the corrosion is very localized in pits of only 20 to 30 millimeters, and 20% of all the inspected bars had a mean cross-section of 37%, which results then in this 9% per retaining wall. What are now the consequences if we have local corrosion in our walls? Here you see the moment rotation curve of a retaining wall which is not corroded, so our resistance curve, and we then can seek for the intersection point with our action, with the earth pressure at rest, or close to it. And let's assume that we then know the moment rotation curve of the earth pressure action. That means that if the wall deflects, the earth pressure will also decrease. If we now have corrosion just here at the construction joint, we see that the bending resistance and also the deformation capacity of our wall will decrease. The corrosion, by the way, is denoted by this parameter zeta, which indicates the relative cross-section loss. However, for this example here, we would still find the point of equilibrium here at this point 1. If the corrosion further increases, then we will come to the ultimate, the last point of equilibrium, where the wall would just be stable, and for further cross-section loss, this wall in this example would fail. Please note here that this point, the ultimate limit state, at this point the earth pressure is still above the active earth pressure, and therefore the wall rotation capacity is insufficient for the earth pressure to reach the active state. And thus conventional limit analysis is not applicable here without checking for the deformation capacity of our retaining wall. And here I will hand it over to you.
So in the context of our two research projects, we developed guidelines for the safety assessment of corroding cantilever retaining walls, and we proposed a procedure, a verification procedure based on 4 different stages, where for each stage the level of detail increases. In this presentation, we will now give you a quick overview of all of these stages. And we start right away with the first stage, which is the most basic one. It's called triage, and it relies on basic knowledge about the geometry of the wall, such as the height and the thickness, and its reinforcement, and on the material properties, such as the soil properties. We can then determine the acting moment on the wall and the wall resistance, and then compare them to verify the safety of the walls. To do that, we consider 2 different limit states. So first, we have limit state A, And there, to calculate the wall resistance, we perform a cross-section analysis, and we consider the total cross-section of the reinforcement. So the sum of the cross-section of the uncorroded bars plus the residual cross-section of the corroded bars. To do that, however, we have to assume that the corroded bars have no further deformation capacity. So we have to consider the wall to be rigid. And in this case, then the acting moment results from the earth pressure at service level, so what we have right now at this state. Instead, in limit state B, we calculate the wall resistance, assuming only the uncorroded bars. And under this assumption, then we can assume that the wall has sufficient rotation capacity to reach or to unload the backfill to the active state, and therefore the acting moment is then given by the active earth pressure. If one of these limit states is satisfied, then the verification is okay. Otherwise, we can proceed further with a decoupled analysis, where we determine the load deformation behavior of the wall. And you have seen before that this depends on the corrosion degree. We further define the earth pressure evolution, also in a decoupled fashion, without considering the behavior of the corroded wall. And then we can superpose these two curves. If then we find an intersection, the verification is okay, otherwise it's not. And to study the earth pressure evolution, we carried out several experiments where we basically placed a scaled retaining wall consisting of 3 independent sections in a glass wall with a rigid base. And then we backfilled this wall with perf sand deposited in a either loose or dense packing, and then possibly also compacted the soil. And after that, we imposed a rotation of the wall stem about its base and measured the earth pressure evolution. So after the backfill phase, we observed this initial stress distribution for the sample that were really just deposited without any compaction. And we see that we have bilinear distribution, and for loose samples, we have higher pressures. We then also conducted some tests where we deposited the backfill in different layers, and after the deposition of each layer, we applied a static load to compact them, or to actually, rather than to compact them, to generate or to simulate increased stresses in the soil. And here we can see that indeed we had a higher earth pressure featuring a peak closer to the soil surface. And also in this case, we observed that loose samples exert a higher earth pressure on the wall. We then simulated a corrosion-driven rotation, and we measured the moment evolution as a function of this applied rotation at the construction joint. And here we can see that for the dense samples, so the black and the pink curve, we have a fast unloading initially, followed by a plateau, and then an increase in moment here in the final phase. And this is due to the softening behavior of dense soil. Instead, for loose samples, we have also a quite fast unloading initially, and then it transitions to a rather gradual decrease because of the hardening behavior of loose soil. And then at the end, we reach the residual state. At the end of the rotation phase, we then observed these stress distributions on the wall. For the loose samples, we had an approximately linear distribution of the stress, while for the densely deposited soil, we had a bilinear distribution featuring a peak or higher stresses towards the base of the wall because of strain localization due to softening. Based on the experiments, we could then propose, develop, and validate a numerical model, which was based on the soil constitutive model hardening soil with small strain stiffness. And then we modeled the boundary value problem by assuming a linearly elastic wall and a rigid foundation as in the experiment. We then modeled the initial stress state in the backfill by really modeling the layered deposition as you see here in this animation of each layer and possibly compact them. And then we also imposed a wall rotation around the construction joint and measured the resulting moment. As you can see here, then we could validate pretty well the experimental results. Here you see the same, for the backfilling phase at the end, we had the same bilinear distribution as in the experiment, as you can see in the blue curve. And this was for a loose, uncompacted sample. And for the same sample, then we could have a really good match also for the rotation phase.
So we come to the load deformation behavior of the wall, and we will start with this phenomenon that we have seen, that the deformation capacity is decreasing with an increasing cross-section loss. It's a phenomenon which is also known as strain localization. And this strain localization phenomenon can be nicely illustrated by a bare reinforcing bar, like we have it here, which has a reduced cross-section over a small length, whereas the blue part is just always at the original cross-section. And you see here on top the load elongation curve for the orange, the blue part, and then, of course, for the entire reinforcing bar as the sum of these two parts. So we first start with the case where we have no cross-section loss. And in this case, the orange part carries the same load as the blue part, and then the elongation for the whole bar can simply be summed up. If we have then a cross-section loss, this curve here is scaled downwards, and the maximum load is then decreasing. However, this orange part is still at the same ultimate elongation. This is then not anymore the case for the blue part, since the maximum load decreased, and this blue part will then carry only part of its maximum load and then also show smaller elongations. And then if we sum up these two parts, we see that also for this kind of length ratio between the corroded and the uncorroded part, the total elongation will be diminished. We reach a critical point if the orange part is just at the moment of rupturing, whereas the blue part is still elastic or at the end of the elastic phase, and then we see that the entire bar almost completely lost its plastic deformation capacity. And then for further decrease, this stays approximately the same. So if we draw this as a diagram of the residual deformation capacity in black and the residual load carrying capacity in blue versus the cross-section loss, we see that actually the load carrying capacity is linearly decreasing, whereas the deformation capacity decreases much faster. And we see also that this critical cross-section loss, where we actually lose the plastic deformation capacity, is reached for really low cross-section losses. For European steels, this would be at between 12 and 17%. And we remember this 37%, which were found in this pilot study as a mean cross-section loss of our retaining walls. So normally, we don't have bare reinforcing bars. We have these reinforcing bars embedded in concrete. And to have an estimate, and of course, this concrete will then carry partly of the load between two cracks, which further stiffens our behavior. And to have an estimate of the load deformation behavior of such a concrete tension member, there is a model which was developed at ETH at the end of the 1990s. It's called the tension cord model. And we took this model and enhanced it for this small cross-section loss here at the beginning near the crack, and then we came to the corroded tension cord model. Here you see again this tension force elongation curve, and you see this black dashed line, which is the response of a bare reinforcing bar without concrete, and you see this black solid line, which is a bar embedded in concrete, and you immediately observe this difference in stiffness, which is attributed to this tension stiffening effect. And then, of course, with these colored lines, you see the effect of cross-section loss, and we also observe here that for small cross-section losses, we lost our deformation capacity almost completely. So to verify these theoretical findings, we conducted large-scale experiments on retaining wall segments. These retaining wall segments were 1.7 meter high and 2 meter wide and were standing on a footing. And they represented the lowest part of a 4.7 meter high retaining wall. And our testing machine then here simulated the non-physically present upper part of this wall. And the specimens then had a different number of reinforcing bars which were damaged to simulate the effect of corrosion. Here you see the experimental results. This, again, as the moment at the construction joint versus the wall head displacement. This is the response of a reference specimen without corrosion. This is the response for a specimen with a slight corrosion damage of 3% on average. And here we have the result of a specimen with 9% mean cross-section loss, similar as what is the mean cross-section loss in this pilot study. We see that the deformation capacity is now really decreased, also the bending resistance. But the interesting thing is now that these two curves here also result from specimen with 9% mean cross-section loss. So what is the difference? In this curve here, we had a specimen with 3 bars damaged to 30%, and in this specimen we had 6 bars which were damaged to 15% cross-section loss. So there obviously is a difference in the behavior, and is influenced by the number of corroded reinforcing bars. And this you can also show theoretically. Here for an example where you have a mean cross-section loss of 10%, this stays constant, but you once have either a small amount of corroded reinforcing bar or a high amount. And you see that there is a critical amount of corroded reinforcing bar where you have a minimum in the load carrying and capacity and the deformation capacity. And it is favorable either to have a few heavily corroded bars or many slightly corroded bars, but not some moderately corroded bars, if you could say. However, in practice, I think we hardly ever know something about the number of bars which are corroding, and therefore we came up with an empirical relationship which is depending then only on the mean cross-section loss, which you can use as a first guess or a worst case for to estimate this critical amount of reinforcing bars. So the load deformation behavior of the wall can be estimated by first have an estimation on this critical number of reinforcing bars and then evaluate the tension cord model or the critical corroded tension cord model for these parameters, and then actually look at the moment rotation behavior of a slice just above the construction joint. And why is this sufficient? We saw in the experiment that 85% of the total wall displacement results from the opening at the construction joint, and thus it is more or less sufficiently accurate to model the rest of the wall as a rigid body. So if the verification doesn't work in the phase number 2, then we can move on and carry out refined decoupled analysis, where we basically can consider the beneficial effects of a compliant foundation layer, or we can determine the true corrosion distribution along the wall. Up to now, indeed, we just considered a rigid foundation for the wall. But actually, if we consider a layer with finite stiffness below the base of the wall, then already during backfill, we have some displacements of this wall or settlement of this wall, which leads to a rigid body rotation of the wall in anti-clockwise direction. And therefore, we then have a partial unload of the wall. However, it is important to be mentioned in this case that if we want to consider a foundation layer with finite stiffness, then we have to model the backfill really accurately, because indeed, if we only backfill between a temporary excavation support and the wall itself, like here, then we have this displacement field here, which leads to an anti-clockwise rotation in anti-clockwise direction. While if we model an extended backfill, for example, between two walls, where we have to fill the whole space between them, for example, to build a road on top, then we have this displacement field here, which leads to a rotation rather in the other direction. Morelos 2, we assumed that we don't know anything about this about the number of corroding bars. But of course, if we know something, or if we can actualize this number, you could come up with a much more beneficial result for the assessment. And as we heard in the last presentation today, it seems feasible that by doing potential mapping or conducting potential mapping out of the drainage pipe, that you could have an estimate on these numbers of bars which are corroding actually.
If also this doesn't work, then we can move forward and carry out coupled analysis. And here we have observed that actually if just one section is corroded or is more corroded than neighboring sections, then we will have a three-dimensional mechanism in the soil which leads to a redistribution of the stresses in the backfill. And as a result, then we will have a decreased load on the corroded section, which is beneficial. However, this leads then to a moment increase on the neighboring sections, and this is only possible if these sections indeed can carry this additional load. And that's why we then need a coupled analysis where we also consider the wall behavior, especially for the non-corroded sections. If that doesn't work, then we have to design strengthening measures. And the most common measures are normally anchoring or conversion to a gravity retaining wall. And also in this case, based on the improved knowledge gained in our two research projects, then we are able to design more effective measures.
So let me finish this presentation with a question which is often raised, namely if structural monitoring would be possible for these walls. To answer the soil structure interaction and also the potential of structural monitoring, we conducted hybrid tests. This means that uncorroded specimens were loaded until to surface level, and then we started the corrosion damage by drilling several bars. Of course, the stiffness of the wall was then decreasing, and then we also decreased the load as a function of the wall deflection. These are experimental results. You see here for a loose backfill, we have this behavior. For a dense backfill, this one. We started to drill the reinforcing bar at the circle, and the bars were fully cut when we reached the square here. And the conclusions for monitoring was that the deflections due to the corrosion damage is really, really small. We speak about 0.8 to 1.2 millimeters per meter wall height for a cross-section loss of 40% on average. And normally, as we heard, we have 9% at the moment on average for most walls. So these deflections are really small if we compare to other actions like temperature or groundwater. And also, which is not that beneficial for structural monitoring, is that large deflections due to corrosion only occur close to the failure point. So we don't have much time then to react. And if we have an additional load on top, then it might fail in a brittle manner. And another problem then, of course, is that if in the time we install the monitoring system, we don't know the state of the wall. This means actually we don't know this starting point where we are laying on the curve. So this challenges structural monitoring very much, I would say. So the conclusions I will not go through due to time reasons. Let me just have a last remark. Up to now, we only have heard about problems of these retaining walls. They were corroding, and the question arises if we should still build such cantilever retaining walls in future. And David's and my answer would be clearly yes, since the observed damages due to corrosion are consequences of errors made during the construction phase, and they are not consequences of a structural error of the system. So given the regarding sustainability and given the high material efficiency of such cantilever retaining walls, I would say they are still one of the preferred choices when it comes to build new structures. Thank you very much for your attention.
So, thank you very much for the nice presentation. Are there any questions? We have time for just 1-2 questions, because I think most of you want to leave, to be honest. Are there any questions? Please.
Just to finish with you. Thank you very much for this excellent presentation. Very interesting stuff. I wanted to ask you, in most of your analysis, the footing of the wall was fixed, right?
Mm-hmm.
So what would be the effect if it was possible to rotate or to translate? So the effect of soil strength interaction, what would it be?
This is mostly then, as I showed actually in one slide, it would mostly affect the initial stress state or the stress state acting at surface level. So it decreases actually the load on the wall. So it's beneficial effect. But during rotation itself, it's not very important. I mean, of course, yeah, considering it will be less conservative than not considering a rigid foundation.
Mm-hmm. No more questions? So in such a case, I will thank you again.
Thank you.
Thanks.
Please.